Thank you. Any questions? Actually, I only have 20 minutes, so I'm going to zip through this. This is about an experiment that is a work in progress. And there's a branch in the ScalaTest repo which has Scalactic in it called feature EquaSets. That's where all this stuff, the examples are coming from. And it didn't start out this way, but sort of ended up being a project that is attempting to explore ways we could simplify the standard collections library in Scala. So originally, the driving use case was that I came up with this thing called equality for Scalactic because people wanted to do custom equality in their tests and in their production code. And so I had that. That came out in 2.0. And there was one use case that involved collections that was every now and then you would like to have a set of objects where you want to use a different equality than the one provided by dot equals. So for example, you might want to have a set of strings where you don't care about case, right? Most of the times, the dot equals method is fine, I think, and that's what you get with Scala's standard library sets. And just like most of the times when you want to compare equality, you actually, that's the equality that you want. But sometimes you want to customize it. So the way that I've done that when I needed to is I just made a wrapper class. So what this shows is an example of a little wrapper class that will ignore case. So I put a string inside something called case insensitive string, or CIS. And all it does is hold on to that string, and then it has an equals and hash code that doesn't care about case. And so if I put it in a set, what you can see is I've put in lowercase high, uppercase high, and high with 2 spaces around it. And down here, what actually stays in the set is lowercase high and high with 2 spaces around it because it sees high with uppercase as the same or equal to high with lowercase, right? And then here's another one, which is Whitespace Sensitive string. I just trim both sides. And so when you put the same things in a whitespace set, Whitespace Sensitive set, I keep the lowercase high and the uppercase high, but I don't have the high with spaces around it because it trimmed that and sees that as the same as the first one. So that's not too difficult. That's what people do. It's a little bit of boilerplate because you got to wrap it every time. But what's nice about it is that if you try and union 2 sets that have compatible notions of equality, you get an answer. So in the top line, I've took the CI set I made in the previous page, and I union it with another set of CIS, case insensitive strings, and I get the union, right? And then the second line, I do the same kind of thing with whitespace insensitive sets. I can union them and get an answer that makes sense. But if I try to union 2 different sets with custom equalities that are incompatible, it doesn't compile, right? And I think that makes sense. So that's what I wanted to have for this class that I was originally calling EquaSet, which is a set with a custom equality. It was that sort of behavior that you could union it on things that were compatible, had compatible notions of equality, but if you tried to sort of use these set operations, unit, intersect, and diff on something that wasn't the same notion of equality, it wouldn't compile. And there was this, in the Scala Z issues, a few years back now, Daniel Spiewak suggested they do that kind of thing with iSet. iSet is, I think the I stands for invariant. But anyway, that's like a set that has an order. And the way that set works is the order, which is like, has a notion of equality in it, because order says less than, greater than, or equal, right? That gets passed to every method on set, but you don't capture 1, right? So what Daniel was saying is you're assuming basically there's only 1 order for any type. Like if you have an order of string, or if you have like a set of strings, there's only 1 order of string. So probably forward order, but you couldn't have a reverse order one. And that's called type class coherence. It's something that Haskell has kind of baked into it, that for every type, there's only 1 instance of a type class. And what Haskell does, because sometimes you might want to order strings backwards or order strings forwards but ignore case, that kind of thing, is you make a new type, like we wrapped string with CIS. That's a different type. So now you can have an order of that type, and it could be different. So I always felt that was backwards, that that it just makes more sense that there's one string and you have a custom order or a custom equality. And that's sort of what people ask for in ScalaTest, and so that's what I put into Scalactic. So what I wanted to do was kind of what Dan was asking for but didn't get in Scala Z. And one of the things I had a hard time figuring out was why people liked type class coherence. And it took me actually a lot of asking different people, why do you like that? They couldn't really at least explain it to me until I saw this talk. This Ed Komet gave a talk called Type Classes versus the World, where he gives a really nice, he actually explains the answer to that question, is why they like it. But he talks about the trade-off. There's pluses and minuses, but there are genuine pluses that I would point you to this talk if you're curious why that's a good thing. But what I'm trying to do is go in the other direction, right? So there's pluses and minuses in my direction. And I hadn't actually gotten around to trying it yet. And Martin Odersky, it was probably a year ago, he came to visit and we were driving up Mount Diablo. And I kind of was telling him I wanted to try this, and he said, well, you know, the way I do that. And so he sort of planted the seed in the brain of using a path-dependent type, right? So the way it works is that this orange object here over here is kind of like you make an instance of that, and that captures the equality. So that's where you capture it. And then that's why I have a little arrow pointing to this equality object up here. That's the equality of E, whatever E is. It could be an equality of string, equality of int, equality of fruit, whatever you have. And then the set is actually like an inner class inside collections. So when you create an instance of set, you have to create it from the path to the collections object. So if I have this val ci, which is a reference to that orange object, I can say ci.set. And I'll get a set that has like it has an enclosing reference to its enclosing object, its outer object. And that set is also got a type parameter. So at first I didn't have that one, because if you create a collections of string, then I don't need to say string down here again. But I don't know, 4 or 5 months ago, I realized that actually that could be a subtype of that other one. So now there's two types. There's the equality type that's in the collections object, and there's the element type that's in the actual set or map or seek. And originally it was just sets, because sets have a notion of equality baked into them. But then there's also maps have a set of keys, so there's sort of a notion of equality there. And later, so we actually made an equimap also, but later I realized that seek has 4 methods that have a notion of equality baked into them. Distinct, which says if I have 1, 1, 1, 2, 2, 2, 3, 3, 3, dot distinct will give you a list of 1, 2, 3. It just gives you the distinct ones based on that all those ones equal each other. And also there's a union, an intersect, and a diff method on seek, which is multi-set union. So it's like a bag. It's like, sort of like poor man's bag or poor man's multi-set in Scala. Those also have a notion of equality. So it ended up not being about sets, which when I actually wrote the thing for this talk, I called it about sets, but it's really about collections, and it ended up being a sort of an experiment to see, you know, what would collections look like if they did this, right? Okay. So I'll just do a demo at the end, but basically I import Scalactic and string normalizations. String normalizations has things like lowercase, that is a way to normalize strings by lowercasing them. It has trimmed normalized strings by trimming off the white space off the ends. And I can convert that to a hashing equality, which I need for the collections object. Because in a set you need a hash code, right? And the hash code has to be consistent with the equality, so you need a hashing equality. There's also a ordered equality for sorted sets and sorted maps. But so I create an instance of collections, and I say this is going to be a collection of what CI points to is an object that sort of defines a family of collections where they're always going to be strings. That's what you can put in there, and they will ignore case. And so like if you make a list in there, if you said call dot distinct, it would make dot distinct by ignoring case, right? They always use that equality that's captured. The second one is WI. That points to a collections object that defines a family of collections that will not care about white space at the ends when it's determining equality, right? So then I can just say ci.set, and here I say hi, 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 where because this is case insensitive, if you look at the what you get, it doesn't take the capital HI because it sees that as equal to the lowercase hi, just like that previous example. And then when I do it with wi.set, takes the lowercase high and the uppercase high, but doesn't take the high with spaces around it because it sees that as equal to the first guy, right? So that's actually what I was originally trying to get to. It's just a little less boilerplate. But what's nice is that I can union two sets with the same notion of equality, right? This is the same example. I take a CI set, that old CI set that I made before, and I union it with a new CI dot set with ha, right? And I get hi, hi, ha, ha, right? I don't get the capital ones. When I union two WI sets together, I get the lowercase and the uppercase, but I don't get the ones with space, right? And if I try to union two sets of strings from different families that have different notions of equality, it doesn't compile. You did type error. So that's that WI.set. The WI part is the path. That's one of those path-dependent types in Scala, and that's the part that doesn't match up. So it's using the path-dependent type to get that compiler error when you union diff or intersect. Okay, so that's part one. And one of the things that I did is I didn't just do that. I started like thinking about, well, what else could we do? I mean, what would make the standard library simpler? And I don't know how we would get there, but so this is just kind of an experiment. It'd be working code people could use if they want, but I think most of the time people need to use a standard library. So this is more like an experiment to try ideas out. One of the things that I found was, let me back up to my picture here. I put a little plus sign there. That means sets are covariant. So I made sets covariant, which is the opposite direction that a lot of people want to go. In Scala, lists are covariant, and sets are invariant. And so if I say, this is just regular Scala collections, if I create a list of oranges, you can see that first line makes a list of orange, and then I try to const an apple in front of it, then it will infer the least common supertype of those two, which is fruit. So I'm going to back up one page and I'll show you the hierarchy here. At the top there's fruit, and then there's a subclass orange and a subclass apple, and then a subclass of orange called Valencia, right? So when I had a list of orange and I const a list of apple into it, it found the least common supertype, which is fruit, right? So I get list of fruit, which is kind of nice, right? But then the problem is the last one, when I const 88 in front of orange list, I get a list with 88 and 2 oranges in it, and that's a list of any, which is probably a bug. So usually when we infer any, it's probably a bug. So this doesn't catch the bug, right? But it does allow us to, the second line, I think, is something we probably do want. That's probably okay. So Scala sets are invariant, and the reason they were invariant, well, what I had to do to make them covariant is pull out that they extend function 1, and that's mixing two different notions of set. One notion of set is extensional, which means I list all the elements. And the other notion is intentional, which is I give a function that says true or false. Is this a member? And it sort of combined them. And when you do that, the way the types line up, you have to make it invariant. So by pulling that out, and I have a separate class called membership, which sort of is the intentional set, the function one. And then the regular set can now be covariant because then it's consistent. So when we teach Scala, people understand that, covariance of lists, that if you ask for a list of fruit and I give you a list of apple, it should work because a list of apple is a list of fruit, conceptually. And they don't understand why sets are invariant. They always ask about that. So I thought it would be better, simpler, if it was consistent. So this is the direction I went. But here's Scala sets. If you make a set of orange, if I try to const an apple, I can't because it's invariant. It has to be a set of apple or a set of fruit already. So what I'm going to have to do is actually map it. This is how you do it. I map the set of orange to set of fruit right here, and all I have to do is take each element and say, oh, this is a fruit, which it is, right? So all I'm doing really is copying the oranges over here to over here in memory. It's the exact same oranges, but now it's a set of fruit. And then I can add apple into it, right? And that's a bit of code. I mean, there's code that you have to do, but it's also if you have a million oranges, like you're doing big data, and you need it to be, you're going to have to actually copy a million over to another memory location just to get it to be fruit. It's kind of, it seems wrong. So anyway, what it turned out is that the methods like plus that has, or contains, that has this type bound that says it needs to be the element type or some super type, in these collections, it also has an upper bound, which is the equality, because if I have a collections of fruit, I only know how to do equality for fruit. So you can only have fruits in that family of collections of fruit in that family. So that actually has sort of a bound to this problem of inference. So I'll show you an example. If I create a collections of fruit, now I have FR is this, refers to this orange object that defines a family of fruit collections. And if I create a set of Valencia in there, so it's under that path, so it's a fruit.set or fr.set of Valencia. If I put in orange, you get a set of orange, so it goes up, goes up the hierarchy, infers the supertype. If I put in an apple, it goes up to fruit, right? But what's nice is if I put in 88, it doesn't compile. So that goes up to the place you like, but doesn't go to where you don't like, right? So it's an upper bound for that kind of problem. So what I had done last year, or like the last couple of conferences ago, I showed you can use static analysis to find any inferences and like contains checks, these things that have this problem of inferring any and actually masking bugs. You can find it with static analysis. But this is, partly, in the type system, you get it within the family that you have, but you don't get it above that. So that's just all in the type system. Okay, so that was nice. So it's this guy right here. That's what the type bound looks like. U is the new type that's inferred when I plus something into a set, or call.contains, right? T is the element type, so it has to be the element type or a supertype. So if you're orange, it has to be either an orange or a supertype of orange, which is fruit, or supertype of orange is any, right? So that actually, any works for that. But it has to be a subtype of the equality type. So since we have an equality of fruit, then that's the top, that's as high as it can go. Okay, so, and then there's something called default, which gives you, I just say collections.default. I get a collections of any. And so if I import that, it really feels like you're using Scala standard library, because that's what this does is it uses default equality for Scalactic, which is always dot equals, except for arrays, it calls dot deep. So the only difference between this and standard collections, well, as far as how the equality works, is arrays. You get structural equality arrays. If you put two arrays into a Scala set that have 1, 2, 3 in them, they'll actually stay 2 because it thinks they're different, because they're different instances. If you put it in a Scalactic set, default set, it will just have 1 because they have the same structure, same elements. Okay. And it will infer any, right? Because now the top is any. So it will actually go all the way to the top, just like the standard library. So, so basically that is my talk. There are a couple other things that I didn't have time in 20 minutes to talk about. But any questions? Why don't we talk about questions? Yes, Eric. Yes. And that's one of the things I didn't have time to talk about, but I can demo it. I'll show you. Let me grab these guys, I guess. Can you see that? Yep. So I have that WI set. Let's map it to something. I don't know. WI set dot map underscore dot plus space Eric. Is that how you spell it? I never know how you spell it. Hi, Eric. Hi, Eric. Yes. So we'll just say dot length. And what the key here is that this isn't a set. It already is lazy, right? So the reason I did this wasn't, one thing is you can make, there's some performance in, sometimes you can make things perform better by analyzing these lazily chained things. But the main reason I did that was because I think can build from is nice and makes things nice, but it's just too much in everybody's face. And if you make map lazy, it doesn't need can build from anymore. There. The only place you need can build from, you don't even need it on sets either, is here when I force it. And I'll have to force it into a set of int, which I don't have. Let me do the other one. If I force this into a set of int, let's say val ss equals and ss.force back into the let's put it in the WI set. We'll put it in a different one. Okay, let's put it into a not CI set. I need to put it into WI. I have to put it into the family and get rid of that guy. So basically, when you force it, you have to. That's when you tell it what family you're going to, and that's when it does the weird thing. But you don't need a functor for that. So you can get a functor for this set just fine. And what I did differently too than the standard library is, if you look at this set, this view, it actually forces. It actually. The times you want to look at the toString is REPL, test failure, log message, debug message, and you always want to see what's in it. So the standard library's views won't show you what's in it because, why, they're views, you know. But I think that makes it harder to use, because when I show map, when you teach people map, they need to see what happens. So that's another difference. There's a bunch of stuff in there like that that I didn't have time to talk about, but I think if you look at the Scala doc, it's just really clean. There's no can build froms. But it's still, like if you have map, it could still do the thing where if you map it to another tuple 2, you get a new map. But if you map it to an int, you get a iterable or whatever. You can still do that same trick. Anybody else? Yes? Yeah. Yeah, because that returns a hashing quality of string. Yeah. Yep. Anybody else? Yes. Well, I mean, people aren't used to it. So when I saw path-dependent types, I didn't know what to do with them. And then over the years, we found things. And I think this is a pretty good use case for them. And what I think is, I mean, I can show you if I just import collections.default. Now I'm going to hide these other ones. _. It's just like using Scala. It's very. I mean, this is Scalactic collections. You can see the type. The type's kind of hairy, right? You have the path in it. Collections is actually an object. No, I'm sorry. Default. Collections.default is an object. That's like a val, and that's your path. And then immutable inhabited. So that's another thing I put in is that for immutable collections, you can. It's in the type that it's non-empty, if it's provable. I think that's useful and simple. So that's where that inhabited comes from. If I subtract something out of here, like 2, then I can't prove anymore that it's non-empty, so that part goes away. But if I add something, then I know it's non-empty, so that comes back, that kind of thing. So anybody else? Going once, going twice, gone. All right, thank you. Oh.